Today, we're going to build a lithium-ion battery storage system for my solar farm using reused second life battery cells and cheap controller components. But before we start, a word of warning. I will be using bare lithium-ion cells. These are standard 18650 laptop style cells. These are not as volatile as lithium polymer cells as you'd use in our C-cars, but if you use them wrong, if you mistreat these can still very quickly cause a fire. So if you decide to recreate a battery storage system based on what I'm building today, please make sure you know what you're doing, get someone who does if you're uncomfortable with them, and as always, proceed at your own risk. So let's get started with the build, but this one starts up on the roof. So up here is my solar farm. You can see the panels that have been up here on the roof for a couple of years and the ones that I've added last year. But in fact, this side of the roof is just 1/6 of it. If we walk up just a tiny bit, I can show you that there's another identical array basically on the other side, and the entire garage is also full of panels. So in total, this is 100 panels in the standard 1 by 1.6 meter size, making up 30 kilowatts of solar power on the roof. This is an east-west system, so it's not super efficient, but it makes a great case for using the power yourself. It's ridiculous how cheap this stuff has become, to a point where the panels themselves are actually cheaper than the hardware, the mounting hardware they need for installing them. And by the way, even on an overcast day like this at 5 p.m., it's still making almost 8 kilowatts with no sun visible at all. I think that's pretty great. And then from the roof, that power goes into these inverters. This is the newer 15 kilowatt inverter. It basically just takes the power from the solar panels and turns it into 3-phase AC that can be used throughout the house or being fed into the grid. There is another 7 kilowatt inverter over here. This is my original one. And there is also a battery inverter and battery storage up on the wall. Now, this system works. It's been working since 2017, if I remember correctly. But there are two problems with it. First of all, it is rather inefficient because this unit takes the AC that the inverter produces, turns that back into DC, and then I believe there's another converter in here. And when you want to use that power, it takes that DC, converts it back into AC, and then pumps it out to whatever consumer is actually using the power. So what I want to do is I want to take out those extra conversion steps and use the power right where and as it is needed. And also, this battery isn't quite large enough. Between AC working in the summer or that same unit working as a heat pump in the winter, gaming computers, TVs, all sorts of stuff, this just doesn't last through the night, especially on longer nights in the winter. So we're gonna add some more storage, and this is where it's all gonna happen. So I managed to buy 1,000 used lithium cells, basically your standard laptop 18650 cells, for an incredible price. These are cells that came out of used e-bike batteries that were reworked to have more capacity or just to have fresh cells in them, and I paid overall, I think, 40 cents per cell. Compare that to $3 to $7 for these cells, for one of these cells new. That is an absolute steal. And most of these cells are actually still in really good shape. These don't even have weld spots on them, and they're supposed to be 1300 milliamp hour cells, and they're still 1400. They're better than new. I mean, look at this. The poor soul that I bought these from has individually measured, well, fully discharged and recharged each of these cells, printed a sticker, put it into a data sheet for 500 cells. It takes like half a day to charge and discharge one of these. They might not have the energy output anymore or the energy to weight ratio that it would need for something that is going to move around like an e-bike, but they're still very good for stationary storage, as I'm going to build. These are going to end up in 96 cell configurations. I've printed these holders. Yes, you can buy these, but if you custom make them, you can make them exactly as you want them. There's going to be 6 in series with 16 cells each, and I'm going to be mixing and matching cells in each of those 6 serial configurations. And as long as you keep each of those 6 battery modules that are going to be in series identical to each other, it's going to be fine. And all of this is going to be controlled by a master PCB, by a custom PCB that is designed just for this application. And after I had soldered up a custom breadboard solution, That took me like 3 hours to make and still wasn't fully functional. I just decided to call that quits and order from this week's sponsor, JLC PCB. In fact, I had already ordered 2 revisions of the main board for these packs before I was even talking to JLC PCB of sponsoring this video. And I think it's fantastic these days that you can just, go into your favorite PCB designer, whip something up and order it for a fraction of the cost that your time is worth soldering up a breadboard solution like this. So these guys have current sensing on them. They have these switching outputs for fans and relays. They've got the plugins for the ESP32 modules that I'm going to be using. There they are. These are going to go in here like that. And overall, I'm really happy with what I got. So I think I paid about 65 bucks for 5 PCBs with 2-ounce copper, the SMT already populated. And I think that is what's great about JLC PCB. They offer PCBs starting from $2 for 5 PCBs. On top of that, they have affordable shipping. They don't charge you for SMT assembly. They just charge you for the components that you put on there. And overall, just having the option of getting your own PCBs made in a reasonable time for a reasonable price, it's just something that enables so many more options. So again, thank you to JLC PCB for sponsoring this video, for sending over a customized t-shirt, and for providing a great service that I personally are very happy with. All right, let's get these packs welded up. So that is one of the modules done. I did give all the cells a quick measure and they're all measuring at about 3.72 volts. So that is perfect. For welding these up, the spot welder worked really well again. And by the way, I am using a fume extractor because this nickel band that I use to weld these up does give off like tiny puffs of smoke, and that's essentially vaporized nickel. And you don't want to breathe that. Now all that's left to do is to keep welding cells into these modules until they're all done. So that is all the electronics of the battery wired up to itself. None of this is live yet, so it's not attached to the cells. But we've got the active balancer, we've got the passive balancer, and we've got the battery protection board all hooked up. I've tested it, all the connections are solid. It is a bit tight, so this is going to get a slathering of hot glue and a layer of Kapton tape just to make sure it's not contacting anything else in the case when it gets slid down in here, and to make sure that over time it also stays where it's supposed to be. That was a bit of a shocker just now. You know, the last thing you want to smell when you're soldering up a battery is burnt electronics or hot, steaming electronic plasticky components. Turns out it's not the battery, it's not the cells themselves that were causing some issues here, but one of the ICs from this active balancer burnt up. I mean, these active balancer boards, they're not getting the highest ratings on the internet from the first place, and I don't think it's actually going to do all that much because it's not very precise in balancing these cells. So I'm just going to leave it out. I'm going to use the passive balancer only, and I'm going to do some software trickery to make up for the lack of this. Yeah, let's just close this one up so we don't have to look at that anymore. If I were to build this again, and I will build this again, I would definitely account for a bit more space to leave for wiring and for the electronics, which did not fit where I originally intended them to fit. But from the way I built this, I believe it is safe. Also in the long run, like all the insulation distances are there, there's nothing being pinched, the protection electronics are in there. So while it is not pretty, I do believe that it's safe and it's serviceable, though if you were to build one, you know, build it a bit nicer maybe, you know. So that is the converter and command unit all built. All these components were working before in a test setup, so theoretically I should be able to just plug in the battery, adjust all the input and output currents using a dummy load, tooled heater PCBs obviously, and then this should be ready to go into a computer. So let's go ahead and try and plug this in. No smoke, but also no function. So that was a comparatively simple fix. It was just a pair of wires swapped and the protection electronics in the batteries triggered, so there was no current actually arriving in the electronics. Now, there is one other problem that we need to address, because as is, this wasn't really working. It's already fixed, so let me explain what we actually built to help you understand, how this thing works. So this is the entire setup that we've got in these two boxes of batteries and the control board. This is basically our controller box with the controller PCB that houses the ESP32, a boost converter that charges from 12 volt into the batteries, and a buck converter that reverses that and takes current from the batteries, takes that roughly 22 volts from the batteries and feeds it back into the computer, where computer, CPU, hard drives, graphics card can use that power. Over here we've got the two batteries. Basically the way these are built with that 7-pin connector is we've got the one main battery with the electronics in there, with the protection stuff and balancing hardware, and then the second one is basically just more cells in parallel. Now the core challenge with these two converters is this. These are constant voltage, constant current converters. So not only do they try to output a constant voltage, in this case, the maximum charge voltage, which is 24.6 volts, 4.1 volts per cell, or on the other side, 12.5 volts, which is the upper end of the allowed ATX 12 volt spec, but also do they limit that current. So if the 12 volt rail in the computer would be drawing more than the 15 amps that this converter is set to, it's just going to slowly taper out and let the internal power supply take over, and the other direction from the power supply charging into the batteries. We do want a limited charge current, first of all, to not overload the batteries, and also to not stress the power supply in the computer too much. The thing is, the way that these are measuring their current is not up here where you would expect at the positive rail. Instead, what they are doing is they've got a sense resistor in the ground loop, because that is simpler, cheaper to do instead of measuring up here at the positive rail. Now, the problem here is that these rely on all the current flowing through this resistor down here that is built into the PCB, into the boost and buck converter that we're using. However, if you put two in parallel, now we don't just have the current path through that resistor in the one converter, but there's also a second current path going through the other converter, which is just wired up in parallel. So what I did is I basically cut one of the ground paths here for the buck converter and added an automotive relay in here. Because as it turns out, this boost converter cannot deal with another converter being in parallel. However, this buck converter is perfectly fine with the boost one being in parallel while it's on. So basically, whenever the boost converter is on, we are physically disconnecting the ground path through the buck converter. And now that is working just fine. So there is that relay, which basically cuts the ground path. It is controlled by the controller. And you can see that that is it right here. And thankfully, I did plan ahead, and I did add a pair of switching stages right there where we can just hook up a relay both for the charge controller and the discharge controller if we need two. But currently, we're okay with one. So here is the system all stacked up. All it needs is to be plugged into a computer right now. Now the thing is, the way that this is being controlled is through the ESP32. That has a Wi-Fi connection, and basically it just gives you a web page that, let me show you real quick, that you can manually override the controls. It gives you some status information up top, but basically this is the same interface that my system uses to control when to charge and when to discharge this battery. So the way that this works is basically the entire solar system is hooked up to Ethernet. So both inverters, the battery inverter and the smart meter, are all connected to Ethernet, and I can read all the real-time information from all of those components. And to make use of that data, I've written three specific programs. The first one I'm calling Scrapey, which just pulls in all that data and presents it in a more manageable format. Then I've got Planny, which simulates the next 48 hours, and it basically decides, okay, when is the best moment to charge the car, switch on the dehumidifiers, charge and discharge the battery. And then I've got the RT controller, which is the real-time component, and that switches on or off Wi-Fi outlets, or, in this case, tells the battery, okay, I want you to charge, I want you to wait, or I want you to discharge right now. All this data is also being fed into my Home Assistant install, which then provides me with some nice graphs, and I could make some more use of that data and, do some more advanced stuff with it in there. But for now, my custom system does everything I need it to. So all that's left to do now is to lug these batteries over to the Unraid server, plug it in, and this should be running for the next, decade easily. One thing I'm actually noticing is 750 watt hours is not correct. This is actually There's actually 2 times 750 watt hours because it's 2 modules with 750 watt hours each. So there we go. There is the battery storage system all built and completed. This in total is about 3 kilowatt hours worth of batteries that can easily power the server through the night. Now, obviously, one question that's going to be on your mind is how much did this battery storage cost? Because batteries are expensive, right? The good thing is, because these are used cells and because I'm using relatively simple components to control all this, this cost in total probably around 300 euros. Now, compare that to the commercial battery storage unit that's up on the wall right there. My DIY solution is about 1/10 per kilowatt hour than the commercial one, and I think that is quite fantastic. Plus, it's using components that are basically all reused. This is not mining any new cobalt or lithium. This is stuff that was already used and would have needed to be recycled, ground up, and like this, it just gets a second lease of life. Now, obviously, I still have some more parts to build more of these battery storage units. In fact, up there, there's a bunch more batteries. I've got a couple more of these ammo crates, so I will be able to build 2 more of these systems that will power 2 more computers in the house. I'll build this battery box a bit more nicely. I'll close up the vents and add some 3D printed shrouds right there. And I think the batteries I will also build slightly differently for the next ones, where just each battery has its own protection PCB and its own balancer. So that's going to be improvements for the next iterations of these boxes. If you're interested in the components that I used, I've linked everything in the description below. Obviously, lithium cells is going to be something that's going to depend on your circumstances where you can get those. The files for the custom PCB and the firmware I've also linked below. No warranties on that, use at your own risk. But yeah, if you have any questions on the build, please leave a comment below. If you enjoyed the video, get subscribed, leave it a like, and yeah, keep on making, and I will see you in the next one.